So this is the towers of Hanoi. It is a, let's go ahead and flip this around since this is the way we typically look at it. So it's a children's puzzle game, except actually mainly because you see variations of this in children's toy stores. But it's actually just a puzzle game for anybody. Now, it's actually a particularly interesting puzzle. The goal is to take this stack of discs and move them over to this peg over here, right? Take them from this peg to this peg. Now, I can't just do this, right? You know, that would be, that would be not according to the rules. That would make it a bit trivial, right? According to the rules, we have to keep a couple rules in mind. The first is that we can only move one disc at a time, right? So you're thinking, okay, well, that's not too hard. We'll just stack them up like this, right? Okay, and then do right like that. But no, you can't. So second rule is in place to prevent us from doing that, which is that when we move one disc, we can only move, when we take a disc, we can't move it on top of a smaller disc. So this isn't allowed, right? But this, on the other hand, is, right? You can take any smaller disc and move it on top of any other larger disc. So really the two rules are, you can take, we move one disc at a time, and a bigger disc can't be placed on a smaller disc. Now, surprisingly, this is, now when you start out these puzzles, we generally tell you to start out around size 3. I'll use these ones for visibility. And the idea here is that we want to move this guy over to this peg, right? So we take him, and I'm doing this in reverse, so let's see. So what we want to do is, and really the thought process, the way this works is, once you figure it out, is, to move this guy, to move this bottom, to move these 3 discs over to here, what I have to do is I have to take these 2 guys and get them over here out of the way so that this third peg is clear, right? So if I want, so I got to get these guys, so I got to get this bottom disc here, I got to take these 2 guys, and I got to get them here. Now the question is, how do I get them here? Okay, and the answer is, to get them here, I'll move this guy out of the way, move this guy over here, take this guy, move him on to the middle, right? I'll move this guy out of the way, and then I can freely move this back. Now I have to figure out, how do I move this guy on top of here? Well, I got to get this top stack off to move this bottom disc over to here, and then finally over to here, right? So believe it or not, this is a recursive process, right? So let's go ahead and add one more disc, okay? Now, let's think about the way that let's rephrase this as a recursive problem, right? In order to move, the problem is that I want to move a tower of size 4 from here to here, okay? I want to move a tower of size 4 from here to here. Now, we have a subproblem now. I want to move a tower of size 3. To do this, so let's think about this. To get this tower over here, what I need to do is move these 3 guys out of the way, get this guy over here, right? And then move these 3 guys back on, right? So let's break that up into a subproblem, right? Because, right, the way recursive problem works is that we do we have a hard part, the recursive case, and then we have the easy part. So what I have to do is figure out how to move these 3 guys here, right? And to move these 3 guys here, well, what I have to do is move these 2 guys over here so I can move this guy over here, right? So to move these 2 guys here, these top 2, I have to move this one over here, move this one over here, this one over here, move this one over here, move this one over here, this one over here, this one over here. Then I can move this guy over here. Now I have to take these 3 over here, put this here. So that means I got to move these 2 guys out of the way so I can put them back on top of that, which means I have to move this guy here, which means I move this guy here, which means I move this guy here, this guy here. And now I can move this guy out of the way so I can move this one over here, this one over here. I do this every semester, so you know, it's once you've now, so this is the way, so this is Towers of Hanoi. But everybody kind of understand the thought process that I went through there, which is that to move something of size 5, right, and I'm not going to go through it because it actually takes quite a number of moves to do this, right? I actually have to do 2 to the n minus 1 moves, where n is the size of the tower, right, in order to do this. So to solve for size 5, I have to move, my subproblem is I move 4 out of the way over to here. Now to move 4 out of the way, that's a subproblem of first moving 3 over to here, right? And then to get 3 over here, well, that's the subproblem of moving 2 over to here, which is the subproblem of moving 1 over here, and then over here, and then over here, right? And so now I've solved 3, and then I would move this over here, and so on and so forth. Okay? So let's go ahead and move to the board and put that up on the board. So let's go ahead and I brought a write-out of the algorithm with me in case I forgot it. Because it is a very, very complicated algorithm, right? So let's go ahead. So first we need to figure out our data structures, right? By the way, for your data structures, I would suggest using a peg. Because we're only manipulating the top of a peg, right? We're only ever putting stuff on top of a peg or removing stuff from the top of the peg. What data structures would you use to represent a peg? Stack, right? Okay. All right, so, I completely forgot the other bit for the Fibonacci sequence, drat, which was ways to get around the calculating recursion. I'll get back to that before class ends, so because I don't want you guys to miss out on that. All right, so let's go ahead and so rather than writing a stack, I'm just going to use lists over here, right? We've got lists A, B, and C, whatever. In fact, I won't even bother putting them up. So let's go ahead and solve the problem of what we'll do is that we'll say we've got a function. We call it move. We want to move n from the source peg, right, to our target peg, right? And then we'll list this other peg here as the auxiliary peg, right, to temporarily store stuff, right? That makes sense to everybody? We're going to move n pegs from the source to the target using an auxiliary peg, right? So let's go ahead and this will look a bit different, but that's okay. If there are pegs to move, right? If n is greater than 0, our base case, there are actually so our base case is. So here our base case is do nothing because there's no pegs to move. So for in our recursive case, if n is greater than 0, we want to move n minus 1 pegs from source to auxiliary, so they're out of the way, right? Move them from source to auxiliary, right? So auxiliary will become the target in the recursive call. And we'll use target as basically this temporary storage, right? Make sense?
Isn't it n greater than 1?
Nope. N is greater than 0. Okay. Then target dot append, right? So we'll slap it onto the top of it. This is just a notation matter, but this is push. Append is push here. Okay. So target dot push source dot pop, right? So we'll pop off from the source stack, right? We move these n minus 1 disks out of the way, okay? Then we pop from the source and push onto the target, okay? That makes sense to everybody? And then we'll take those disks that we moved out of the way, move n minus 1 disks, and we'll move them from auxiliary, right? Because we move them to the auxiliary, to target. And we just have to list our other one over here, source. Okay? Now, of course, this is by no means a working program. Obviously, this is a bunch of pseudocode. Okay, it's now a working program in Python. I kid you not, this is the algorithm that solves this problem. It is a very simple algorithm, okay? And it makes sense. We move n disks from the source to the target by first, right, And again, I'll just move this down here. So you move n disks from the source to the target by first moving n minus 1 out of the way to the auxiliary sphere, to the auxiliary peg, moving from our source peg to our target peg, and then moving the remainder over here. Okay, but wait, you say, what about that sub problem, right? That seems a bit hand wavy. Well, in that case, that's the problem of moving n minus 1 pegs from source to auxiliary using this as this temporary storage, right? So what we do is that to do that, we move these guys over to here, to move this guy over to here, to move these guys back, and so on and so forth. And that continues until we have no disks left to move, which is how we know when to stop, right? Because there's no disks left to move. And if you want to try it out for yourself, if you have a Python program, you can find the code. I pretty much lifted this code directly from Wikipedia because that makes it fairly easy to calculate. So your task tonight is to code up a problem, something that solves the Tower of Hanoi for you guys. Now, I suggest going on to, so I'm going to go ahead and change my view here. Whoops. Close the preview. Right. So first off, I suggest going to this website over here called Wikipedia, right? And look up Towers of Hanoi, right? Because I'll say it bluntly, their writing's a bit better than mine. Specifically, well, the rendering is like this beats my handwriting any day of the week. They have this really nice image under there if you need a more graphical representation, which is really cool because you can click on it. It says, hey, so to move this guide over here, we break it into these steps. We move the top 3 disks over to here, then we move this last disk over, then we move these 3 disks on top, right? So it looks really, it's exactly the process I've been saying. So the recursive solution, right, this is the code I was writing up, just I didn't print out my stuff over here, right? And if actually I were to copy this, put it into Guinea, put it over here, save as, let's see, towers.py, and run it, right? It gives me a printout of how this works, the step-by-step that it works. And that's kind of what I want you guys to try your best to do in like 10 to 20 minutes, right? And while you're working on that, if you want to come up and get your exam because you missed it, you can. But this is the other in-class exercise I'd like you guys to work on. And once you're done with this, you can move on to working back on your regular scheduled homework, okay? So, but this is the source code that you guys, but really this is it. Now for your data structure, again, I recommend just creating 3 stacks, and what I would do is just simply print out, right? I'd basically translate this into Java, right? So this would be an integer. These 3 things would be stacks. The if statements are if statements, right? And then here I would actually have 3 print lines, 1 for each stack, to just kind of show the status of each stack. And that's really all you need to do, right? And it doesn't look like it should work, right? But this is what I mean when we've been saying that recursion takes difficult problems and moves them into the realm of something that's very easy to understand, right? All right.